All right, so we are diving into chapter 9, which is exciting because that's technically our last real chapter of the class. I'm kind of checking ahead here to see how many sections. I know I had emailed out how many sections are important, and now I'm forgetting which ones those are, but I will check with my own email as I go through this. Now, quadratic equations, solving quadratic equations by completing the square, I'm going to warn you. I don't like to be a downer, but I'm going to warn you. This is a little rough. And in a way, it's rough. You put in a lot of effort and you don't get back a big reward, meaning some of what we learned today, probably the hardest part of what we learned today is not going to be, it's not going to show up that much in future math. Now, if you keep taking math up through calculus, you will see this again because there are some problems where it just, you get forced into it. I think it's in calculus level 2. But the reason it exists, maybe later, okay? The reason that completing the square basically exists is it sets up what I'm going to assume is section 9.2, the very next section. Yeah. 9.2 is really important, very common, use it all the time in math. So in a way, it's always tempting to skip completing the square at this point, but who knows, at some point in the future, you may need it. So just bear with the pain and suffering here. Now, we need to talk about what quadratic equations are. Okay, so, because that's the focus, that's what chapter 9 really focuses on. And we know what these are without really having talked about it consistently. So they're equations that are led by an x squared. Their highest power of x is x squared. So ax squared plus bx plus c equals 0, with the added restriction that a, b, and c have to be real numbers. Now, when we solve one of these things, we may not get real numbers as our answers, but the coefficients of the x's, the numbers in front of the x's, those have to be real numbers. So, examples, things like this. Here's a quadratic equation, and I'm going to change it because I want to make it something that is factorable, just because we've talked so much about factoring. So here's something that very clearly fits that format. There's other things that fit the format maybe less clearly. Okay, this doesn't look at first glance, it looks like it's missing some stuff, but I can repackage it as x squared plus 0x minus 9 equals 0. And then you can see that it fits the formula a little bit better. We've got, let's see, 1/4 x equals 0. Also fits the formula because then we have 0x squared plus 1/4 x plus 0. 0 being a real number always opens up all kinds of possibilities with how we can format things. Okay, so these are quadratic equations, and right now, notice that we're going to be solving them. Well, I don't know why that would be, Matthew. Maybe it's stuck. Maybe try again. So previously, and I'm going to be very specific here because Chapter 6 is burned on my brain because it was such a long, involved chapter. We had these type of equations and we were solving them in 6.8 left and right, but we had factoring at our disposal. So what happened to factoring? Why aren't we talking about that now? Hang on, babe. Using factoring. So an example of that, since I set this up so cleverly, the very first quadratic equation that I had written right up here, if I were to factor this out, make sure I did that right. So, no, I probably did that wrong. I record these things so early in the morning. It's, well, not really early, but early for my brain. Okay, so. Okay, I am going to make this work because, and I apologize because my videography skills and the time I have at my disposal are not such that I go back and edit these things so you guys get to see in live time. Because I online teach like I in-person teach. You're going to see it all. You can't edit an in-person situation. Okay, I think this is finally going to work out. I think I finally got something. So 2x squared plus 10x plus 1x plus 5. Okay, so then I set these guys equal to 0 and very quickly rearrange things and I get my answers. So, okay, this is great, but what happens if we get something that is not factorable? Which happens a lot. Realistically, factorable polynomials are pretty much set up for our benefit in math classes. If you have an equation that is modeling some sort of real world situation, it's probably not going to factor. So that's the reason for chapter 9. That's what we need here. And as you can imagine, as the numbers get uglier, the methods get uglier. So that's what we're facing today. So what happens if we can't factor? Well, to learn what happens if we can't factor, first, we need something called the square root property. Okay, and let me pause this and check on what my son is doing. All right, so the square root property. Here's what we're looking at. All right, that's the square root property in all its glory. It's very short, very brief. I feel like it requires a little bit of explanation. It is short and it is brief. I'm going to put an example in here that has nothing to do, well, it doesn't have nothing to do, but it comes out of my brain, not directly off the pages of the book. Oops. So here we've got x squared equals 12. Now, in the old days, 6.8, here's what we would have tried. Nothing wrong with the fact that we would have tried this, except that now it won't work the way it did then. Okay, we would have had something like that. And magically back in 6.8, they would have made like 12 would have been like a 16 or something, a perfect square, so that we could have broken this down, you know, like that or something. Now 12 is not one of those nice numbers. So what we say is that x squared minus 12 just doesn't factor. It's prime in the language of the book. Okay, so that's kind of to explain the difference. So now if we put the 12 over there, and then I rewrite the problem so that I don't destroy. Okay, this is going to be my explanation for the square root property. And the good news is you can just memorize the square root property and not worry about my explanation, because it refers to some of the more obnoxious particular points in the book's lingo. So we are square rooting both sides. This is like the opposite of what we did, I guess, the end of chapter 8. Or the end of chapter 8, we had roots that we didn't like, so we raised the equation, we squared both sides, got rid of the roots. Now we're bringing an equation with a square in it down to the square root level. Okay, you might remember, this is the obnoxious part, the square root of x squared has that little obnoxious thing where even though it feels like the square root should just cancel out the square and release the x, technically it does this unless they have been so kind to tell us that x is positive or that x is 0. If they have been, then we're free to say that the square root of x squared is just x. Okay, now I really don't like, they have it at times, and I've probably very clumsily tried to alert us to the fact, they have at times let us know that x is going to be non-negative. Sometimes I find it tucked away in the middle of a section. It's easy for me to miss. They don't make a big fanfare about it. This is not one of those sections. Okay, so technically what has to happen to me is this. And that feels a little bit unsatisfying. It's like we're supposed to solve for x, but we just solve for the absolute value of x. Okay, well, the absolute value of x from way back when, we barely talk about it in Algebra 2, it is a shortcut for the fact that x could be positive, x could be right before I continue talking. We're trying to force this to be a positive number. If it's a negative number, the absolute value bars force the result to be the opposite of what we put in there. So if we put in a -2, what we get is the +2, or the opposite of -2. That's what this negative sign right here is referring to. If we put in just 2, we get out 2. We get out exactly what we put in. Okay, but the plus or minus x thing. Okay, so clearer. Plus or minus x. And usually we consider it more convenient to have the plus or minus part go over with the number, because yeah, it's just nicer. So x equals plus or minus the square root of 12. And the square root of 12, if we break that apart, because 12 is 4 times 3, we've got that, right? Okay. So this is what the square root property is taking into consideration, so that we don't have to mess with absolute value bars or that thought process at all. That's what the square root property does for us. So I'm just going to say it takes care of the details for us. And we jump straight to the answer. Or sometimes maybe we have to simplify the root, but we can move more quickly, more directly to the final answer. Okay, so if you didn't understand a word of that and you feel like this square root or this absolute value thing has just been messing with your mind every time I mention it, don't worry, it's kind of a thing for later on in algebra. Here's an example. And I am going to rewrite that. And as I square root both sides, watch what I do. This is the thing that you have to, this is the trade-off for memorizing the rule. You have to remember that the right side is not just the square root of 18, it's plus or minus the square root of 18, or your problem will not come out correct. Oh, Matthew, look on that table under your Sunday school papers. I think the bells that she gave you are under there. Look under the other papers too. Oh, the big kind, that was packed away with Christmas. All right, so here's what our answer kind of looks like, but we know that 18 is 9 times 2. So the real answer is plus or minus 3 times the square root of 2. We get 2 answers here, which if you think back to when we would factor one of these things. If we had like x squared equals 9, some kind of perfect square, and we could rewrite the way chapter 6.8 liked us to rewrite, and then we could factor we would get parentheses within parentheses, plus or minus 3, like that. So the plus or minus thing has been happening to us even back when we could factor, as long as we had something in this form. We just usually didn't apply that little shortcut, the plus or minus shortcut, because we weren't doing a whole lot of writing anyway. We didn't really apply that shortcut all that much. All right. Practice 2. Okay, so they disguise this one a little bit from us. So if you see that completely out of context, meaning you're not sure whether it's a chapter 9 problem or a chapter 6 problem, the inclination might be to try to factor that, which is not a bad inclination to have, to fall back to that. Well, let's see, I identify a GCF in here of 3, pull it out, but then realize that you can't factor the insides anymore, so you're kind of stuck. Back in chapter 6, if something didn't factor, we could just move on with our lives. Now we can't. So the square root property goes the opposite way from chapter 6. Instead of creating that 0, we move the number part over to be with the 0. We leave the x part on the left, we move the number part over. Let's divide out our 3's. And then, again, I'm just being really picky about not destroying, not writing over too much over the same line. Plus or minus the square root of 10. Can't forget that plus or minus. So x equals plus or minus the square root of 10. And considering that 10 can only be broken down as 1 times itself or 2 times 5, we're not going to find a perfect square hiding in there, so we can consider our work here done. I'm sorry, what, Matthew? The corner box? I'm not sure what you're talking about. No, I think we use those all up and put them all on. I'll have to look in the closet later. Okay, so now we have something where it's not just x squared. It's an expression in terms of x, but the square root property will be handled the same way. Meaning our goal is still to get rid of that second power and release the inner expression. So we are going to square root both sides. And as we do that, out comes an x plus 3 on the left. And we'll have to worry about the square root of 20 here in a minute. We will also have to subtract the 3 over because we want x totally isolated. But I would rather do that as the last step. So let's identify the hidden perfect square inside of our 20. Okay, and when I subtract the 3 over, I'm very carefully going to put it right where my arrow is pointing in front of all that mess. I don't want to have to deal with putting it behind the square root. That's dangerous. So negative 3 plus 4 minus. Okay. Quick, easy, simple, right? Enjoy that while it lasts, because when I flip the page, I know things are going to get worse. But this groundwork that we need for what we're actually going to learn today is not that bad. Okay. Now here, this gets interesting because it brings in the last thing we learned out of chapter 8, which was those imaginary numbers. Now, if you think about the way real numbers work, you can never square something and get a negative, right? 4 squared is always going to be positive 16, not negative 16. That wouldn't even make sense in the world of real numbers, the world we're used to living in. But it's a whole new world now. So we are going to very carefully apply the square root property, remembering what we did at the end of chapter 8. Okay. Square rooting the squared quantity releases my 5x minus 2, just like I wanted it to. And then I've got this plus or minus the square root of negative 9. Let me back up and just do a little bit of a review on that section of chapter 8. The way we handled this was we recognized that negative 9 is negative 1 times 9. And negative 1 times 9 is rewritten that way. Square root of negative 1 is I. Square root of 9 is 3. So the very next step here, what I am going to have, I just wanted to kind of follow that logic train all the way down. I'm going to have 5x minus 2 equals plus or minus 3i. So now we've combined our new square root property with the i's, the imaginary numbers. All right. Remember that numbers that have i's in there, complex numbers, usually fit the format a plus bi. That's probably where we're headed. So I'm going to put this 2 in front, and then I'm going to carefully divide through my 5. Now, depending just the way you're wired, when you divide through by the 5, you might think to do this, which is not mathematically incorrect at all. But remember, the A and the B need to be completely like separate things. So the way that we need to do that is like 2/5 plus 3/5 I. We're just playing their little game, keeping them happy, fitting the complex number format. All right, now, here's where the rubber meets the road. Completing the square. This is the part that you, depending on your path through life, specifically your path through future math classes, you may not ever really need to see this again too much. So I want us to consider the exact same examples that the book has us consider here. These are a series of factorable polynomials. And I'm just going to put them all up on the board, back to back. This one's got a fraction. That may or may not be helpful for teaching purposes here. If I factor these, notice that I'm going to get matching numbers every single time. And the way that we more commonly write this, or the book more commonly writes this to avoid writing the same thing twice, is to make use of that second power. Okay, now these are things that the book actually had a formula for that I had to skim over, skip it away. I think I showed it to you, but I didn't have you memorize it because it just, it can be a little bit too much. There's other things that you legitimately need to memorize. Maybe this is the time in the course where those who have it memorized might see what's happening with completing the square quicker, but I really don't know. I feel like we can handle this without needing to have it memorized. In fact, it might be better to handle it without having it memorized because you're going to be seeing it fresh, and it's going to kind of strike you, hopefully, in a way that it couldn't really have struck you back then. Let me rewrite each of these polynomials in a certain strategic way. And you might be looking at this like, what is she doing? And I said it was strategic, not convenient looking, not pretty. All right, here we go. Now, the thing that I was attempting to get across by writing these three factorable polynomials the way I did was notice this was the same quantity that ended up in the final answer. If -3 was the quantity that ended up in the final answer in this position, well, the middle term was 2 times -3, and the last term was -3 squared. If 3/2 was the number that ended up in that position, well, lo and behold, the middle term was 2 times 3/2, and the final term was 3/2 squared. That is not accidental. These are called perfect square trinomials. And all a perfect square trinomial is something where that little pattern is going to happen. So what we want to do when we're completing the square is forcing this situation to happen. And I'm going to use a little bit nicer language instead of forcing it to happen. Means we're creating a perfect square trinomial specifically because look at the way that they can be written. They can be written in a form that kind of leads directly into the square root property. Okay, so just laying it all out there, that's our goal here. And I want to look at. Oh, I don't have my calculator out today, and I don't know where yours is either. You know where you put it? Okay, good. I'm looking very carefully to see. What did you draw? Oh, that's nice, Matthew. It showed a shadow of you. Let's see. So let me just emphasize the pattern here. I was trying to think of a better way to write this. So we want our variable squared plus 2 times a magic number plus that magic number squared. So I'm going to refer to the number in pink as the magic number. Totally going off script here from the book. Okay, so let me rewrite that down here a little bit nicer. So I'm going to use x to represent the variable. So the pattern is that x squared plus 2 times the magic number, whether that magic number is positive or negative, plus the magic number squared. So, whoa, we don't have a marker there. Oh, that's great. What is it? And the way. Okay. Oh, it's a water faucet? No. It's more like it's. There we go. In terms of the magic number, this is what we've got. All right, so if I can move that on the screen. It's going to look like a water faucet. Try it again, yeah, drawing a water faucet. All right, so we want to solve this by completing the square. We've got. Oh, okay, I see it now. Okay, so I want to solve this by completing the square. Okay, so what I do is kind of lining up here. I'm lining this up a little bit. I'm going to have my variable squared plus what will soon become my middle term. This is the part I'm missing. So I'm going to leave myself a space here, equals 3. The 3 is already there. It's not really part of this at all. Okay, so let's consider here, the middle term needs to be able to be written as 2 times the magic number. So it's the middle term that's really going to reveal the magic number to us. I didn't know what it was before this. So b squared plus, can I write 4 as 2 times something? Yeah, I sure can. 2 times 2. So that means I have identified my magic number. So same idea as I had before, it's just spread out a little bit. I'm going to put an X here. I realize I forgot my second X. Okay, so that means I've just identified it. That is my magic number. So that's exciting. So what I want to do, I've got this equation, and what I do to one side of an equation, I automatically have to do to the other. In order to force a perfect square trinomial, the magic number needs to be squared right here. But if I do that to the left side, I have to immediately do that to the right side as well. Okay, so I have the format here. I have variable squared plus 2 times the magic number with the variable plus the magic number squared. That is automatically 100% of the time, and you could factor this out to prove it to yourself, going to turn into variable plus magic number within the second power there, and I wanted that to be black.
Are you finished?
Oh, not quite. 3 plus 4. And the advantage of going through this craziness is this gets me, this is where a problem would have started a few minutes ago. This gets me a nice squared quantity equal to a number. And I am going to dive right into the square root property here. Plus or minus, can't forget that on the right. Plus or minus square root of 7. Square root of 7 doesn't break down anymore. Let me subtract the 2 over. All right. That's what I get. Okay, so it's a bit of a mess, and it feels a little bit like we're cheating because we're forcing something to be there that wasn't there before. But as long as we obey the rules of algebra and keep our equation balanced, algebra does not care that we reformat this to fit our own purposes. All right, so let's solve another one. P squared minus 3p. Okay, now they've messed with us a little bit. Remember the way the first one started? We had b squared plus 4b equals the number over there, and the number really wasn't part of the perfect square. We have to create that situation here. First of all, and I don't want us to lose sight of the big picture. The reason that we're doing this, the reason that we're completing the square here is that this is not factorable, it's prime. If it were factorable, factoring is always preferable to completing the square. And I know it just shows how deep into the weeds we are that factoring is now considered the easier method. But that's the reason. We aren't just playing with this for the sake of playing with it. We can't get at this any other way. Okay, so let me move the 1 over, make it negative. Now I have to be able to rewrite this middle term as plus 2, always a positive 2, times some magic number. So this is going to feel like artificial and clunky. So this needs to be 2 times a magic number with a p attached. The magic number is apparently going to have to absorb that negative. And then I will need the magic number squared at the end, and then I better go ahead and balance by adding the magic number squared to the other side as well. So that's where I'm headed. Okay, so very carefully consider what would happen if my magic number, let's see if this works, is going to have to be a fraction. Okay. Would this work? If I canceled those 2's out, sure enough, I would have the minus 3 that I started with. So that's good news. So the -3 is what the -3 halves is what's going to be squared and then added to both sides. And if I do that, took time and effort to fit this currently weird looking formula, it will all collapse down, guaranteed. I could prove it by factoring. So I didn't start with a factorable polynomial. I now have one. And not only is it factorable, but it's always factorable in such a way that you're going to see the variable plus the magic number all within a set of parentheses raised to the second power. And I'll keep that pink for one more step. So ugly, right? Now, we don't want to jump into square rooting both sides because this right side needs a little bit of attention on our part. Okay, so this is -1 plus, if we very carefully square both the top and the bottom of our fraction, got that. -1, we can write that as -4/4. We're getting one step closer to having a single item on the right-hand side. And when we have that single item on the right-hand side, then will be the time, like right there. Now is the time when we can safely and productively take the square root of both sides.
What do we do? After this, when we swapping.
We will? Okay. Okay, so P minus 3/2 out that comes plus or minus the square root of 5/4. Are we done yet though? No. We have to go. I see that 4. I want to dig a 2 out there because I know it's not really just 4, it's the square root of 4. So using the quotient rule for radicals, lovely to have to bring in some chapter 7 in the middle of all this, right? That's what I'm facing. There. Last step, add my 3/2. Okay, we're good to go. Okay. And yes, they went there. Okay, but they went there for a certain reason here in this next example. Okay. Now, yes, we will have to subtract that 1 over, but there's some other problem here. The format that I had written out, x squared, or the variable squared, plus 2 times the magic number, times x, plus the magic number squared. There was a 1 in front of x squared, and that absolutely has to happen. Look at all the examples here. X squared, x squared, x squared. There's not a 2x squared, a 3x squared, a 5x squared, nothing like that. So if we see that happening, the first thing, unfortunately, we need to do is we need to divide everything by whatever is preventing the x squared from being next to a 1. So we need to divide by 3 to both sides. X squared. A few more minutes, Matthew, you're doing good. Okay, plus 1/3 equals 0. And unfortunately, that creates a fraction. Even more unfortunately, when I set myself up for the completing the square, it's a negative fraction now. Okay, so what I want is x squared plus 2 times a magic number with the x. Can't forget the x like I tend to do. Then we want plus magic number, whatever it is, squared to both sides. And of course I had, well, there's a more streamlined way I could have written this. But here's what we're looking at. We want to rephrase -4 as 2 times some magic number. Then that magic number will become the focus of the rest of the problem. And thankfully 4 is a whole number. So 2 times -2, -2, -2, there it is. Magic number squared, magic number squared. Okay. The minute that we rewrite like this, we can collapse the left side of our equation into something squared. And I'm going to rewrite the rest of it that's not pink here. X plus the magic number, but writing plus -2, we don't usually do that. Here we go. Here's where we're sitting. Can't apply the square root property quite yet. The right-hand side is too messy. Okay, so this is -1/3 plus 4, apparently. And I'm going to call that 4/1 because I'm looking to get myself a common denominator.
That's not the way.
12/3.
Not the way.
Well, bring it here if you can't get it to erase, and I'll erase it for you. All right, so 11/3. Here it is. It's beautiful. And they're really just going for the gold with this problem. Right. That's my erasing etch a sketch here. That's something I need for my computer. Okay? Yeah, we can't play with that. Here, here, etch a sketch. I erased it. Now it's all gone. All right. So. (11/3). Now, here's the bad news on this problem. Recall, if I break this apart, there's no perfect square there, but recall that we have a square root in the denominator, and currently algebra doesn't like that. So we're going to rationalize another blast from the past, chapter 7, like that. They are just really, really incorporating everything we've learned recently, since right around a little bit before Christmas and since Christmas. And now when I add the 2 over, now they do something in the book's corresponding example that bothers me a little bit, and I guess would it have applied to a previous, not really. Yeah, I'm going to go ahead and do this. The book would have written like this. They are setting us up for the way that problems are going to look in section 9.2. This is not even a wrong right thing. This isn't even really like an A plus BI format that we have to conform to. So I am going to stick with, when I get my answer, by George, that's my answer. The book prefers, let's see, that would be if I got a common denominator. That. So just bear that in mind if you're checking answers with the book at this point. I get what they're doing. And I get why they're doing it. But there isn't, if there's no I in the problem, there isn't really a need to be conforming to a specific thing. We got to bring it over here, Matthew. I'm working on my last couple problems. Okay, for good measure, we've got one that is probably going to incorporate some imaginary numbers. Me too. Well, I can't draw right now. I can erase for you. I can draw for you in a little bit. Okay, do you need me to erase? All right, let's start out by dividing our 2. Get that 2 out of our lives. Okay, erase that. I'm almost done, and then we'll do our cooking, and then maybe it'll be warm enough to go outside. Okay? A few more minutes. All right, so this is where we are when we get rid of the 2. Then we push that 7/2 over to the right side. Now it's negative. All right, and what we want, as always, let's see if I can be slicker about how I present this as I change colors left and right here. So we want -5/2 to be 2 times some magic number. We've got the x there. We want some magic number squared and added to both sides. Okay, that's our goal. Because it was a -5/2 and we've got a +2, always a +2, the magic number has to incorporate that. And I'm just going to state it for you guys. Messing with these fractions can be strange the first time. Note that the 2 would cancel down into the 4 and we'd be left with -5/2. Okay, and then we've, like I said, halves.
That's so cool.
And got that. We've got that.
When did you like that?
No, I don't need to right now. All right, so x something squared. Trying to be clever again here as I stay with my pink marker.
There's a marker.
It's just a kind of pretend marker there on the screen. Okay, here's what I'm sitting at. That's pretty bad. Having to recognize that 2 times -5/4 would get us our -5/2. All right, but we're past that point now. All right, if we square -5/4, we get 25/16.
I want to slow this.
Let me give you a piece of paper, and as long as you keep it on the paper, this is Play-Doh, then we can Play-Doh. You can take it out and play with it, and you can smell it. All right, -7/2. I'm trying to make it have a common denominator of 16. So this is taking more thought on my part than a couple of the previous common denominator problems. 8 times 7 is 56. Okay. We are getting there. Well, don't taste it. Yeah, we don't want to eat that. That's not. I don't even think that's regular Play-Doh. Honestly, it doesn't smell like. I think his Sunday school teacher might have made it herself, which is really cool. But it does not smell like the Play-Doh that I'm used to. So notice I have a squared quantity equal to a negative. That's a huge clue that imaginary numbers are coming.
Can I smell it?
Yeah, you can smell it. You like the way that smells? Okay. Now, here we go. With great caution, let me break apart that. The 31 can't reduce, but having that negative under the square root means that an I can come out. So I've got this. Plus or minus, remembering that I's always go in front of square roots just in terms of formatting, not for a wrong, right reason, just to avoid danger. And here you will, I'm assuming if the book is going to be at all consistent. Oh, and then here I fall victim to different books that I have taught from. The book, I believe, the last book that I would have been teaching from in the college would have kept it like this. Our book doesn't care, apparently, that it's I's, so basically, if there's instructions at the beginning of a problem about the format to leave it in, adhere to those instructions. If not, you have a little bit more leeway, and that's great. Now, I need to check the email that I sent out.
Where's your calculator?
Oh, I left it in the office.
You can use mine.
Well, that's very nice of you, Matthew. Thank you.
You want to? I'm gonna go get
Okay, perfect. Let's see. Through example 8. Okay, so I guess yeah, at this point, I wanted to leave off example 9. It's an interest problem. We've done a few interest problems. Thank you, Matthew. We've done a few interest problems. It's not bad to look at example 9, and I'm tempted to just add it as extra bonus, but I'm going to stop here because I want to keep our brains on completing the square and not distract them with a word problem, even if it is useful. Word problems about interest are useful in real world and such, but we just learned completing the square, and it had like a bunch of stuff in there from chapter 6, chapter 7, chapter 8. So I think I'm going to go ahead and, it's like, I would say quit while we're ahead. I'm not sure if we're ahead after that, but comfort yourself with a lot of that is not, I think I had put in the email, that's not necessarily something I would have put on a test for this, because what comes after it is what it's leading to and what is more important, more common, and even easier, I would say. So let me stop this and we will just call it quits for today.